Hello everyone, my name is Cameron Bundy and I'm an applied mathematics major here at Central Washington University. I'm excited to share with you some of my current research conducting numerical analysis on Mount Baker snowfall data, which I have been working on in my numerical analysis class with the help of Dr. Brandy Wiegers. Just a little background on Mount Baker and what makes it so amazing. Mount Baker is located in Washington State, just 53 miles east of Bellingham and 86 miles southeast of Vancouver, BC. Mount Baker is one of the first places in the United States to allow snowboarding, and Mount Baker also holds the world record for the most snow at any ski resort. Mount Baker is generally regarded as a special place for skiers and snowboarders alike due to the extremely high snow levels compared to other Washington ski resorts. In many cases of research, there's an underlying issue or dilemma that we are trying to observe. In the case of this project, I'm curious if these high snow levels will be affected by climate change in the future. According to an article observing the future of Washington State ski resorts, Mount Baker is the only Washington ski area that does not utilize snow machines during months of low snowfall. Snow machines are commonly used at resorts such as Stevens Pass, Snoqualmie Pass, and White Pass. Something I found interesting was that it was only in the last decade that any Washington ski area began using snow machines. This article also goes on to project that within the next 50 years, we will see a huge decline in the overall snow at resorts, and will be using snow machines for the majority of their ski seasons. I've attached a citation at the end of my report if you're interested in learning more about this, but for now we will continue on by studying some of the Mount Baker snowfall data. The goal of this research is to analyze Mount Baker snowfall data in hopes of better understanding yearly snow conditions, while possibly even forecasting future Mount Baker snowfall levels. I will create multiple interpolating polynomials using Mount Baker snowfall data going back 50 years to see if the resulting polynomials can help us model the data. Will these high snow levels continue in the future? Well, I hope by conducting this research, I might be able to answer that question. The data starts in 1970 and goes to 2021. The data was recorded at the end of every winter season and is the total accumulation of snow in inches. We can see the highest snow level was in the winter of 98 and 99 up here, where Mount Baker saw a season total of 1,140 inches. Pretty amazing. The lowest snow accumulation was in the winter of 80-81 down here. One question you might be wondering is, what is an interpolating polynomial? Well, an interpolating polynomial is a polynomial that passes through the desired points of the dataset being observed. Some common interpolating polynomials are Taylor polynomials, Lagrange polynomials, Hermit polynomials, and cubic splines. Interpolating polynomials can be very useful in numerical analysis to help analyze behavior of data between points, or in some cases, might even be able to help us forecast the behavior of future data. We will first begin our interpolation analysis by looking at Lagrange interpolation. This interpolation technique was named after French mathematician Joseph Louis Lagrange in the late 1700s. One really nice property of the Lagrange method is that it does not require data points to be equally spaced, which can be really nice if you're dealing with time series data and maybe have some missing years in the data set. This method can help give an idea of what those missing years might look like. Fortunately for us, all the snowfall data is equally spaced and is not missing any years. Overall, the Lagrange is relatively easy to construct and can even be done on paper, but for this research, since the polynomials are interpolating so many points, the functions were created in a Mathematica program. It is worth noting that the degree of the Lagrange polynomial is always a 1 less than the number of points used in constructing it. Now let's take a look at what a Lagrange polynomial looks like graphically. Instead of using all 51 data points, only 16 of the points were used in constructing this Lagrange, giving us a 15th degree polynomial, which can be seen here in the top left corner. This Lagrange polynomial does not give us an accurate depiction of the data at the endpoints, as you can see. The Lagrange actually drops into the negative values, and since we can't have negative snow levels, this wouldn't make sense. But if we observe the polynomials between the years 1983 and 2011 on the plot in the bottom left corner, it looks a bit more natural. We are seeing a lot of unrealistic behavior at the endpoints, which can be common when trying to force fit the data to a polynomial. higher degree polynomials tend to oscillate a lot, which can make them unfit when numerically analyzing data. We will now move on to another interpolation technique called Hermit interpolation. The Hermit interpolation method was named after French mathematician Charles Hermit in the late 1800s. The Hermit interpolation formula is a bit more complex, and although it can be done on paper, it's not very practical unless there are only a few points in the dataset. The Hermit actually builds off of the Lagrange formula, so once you understand the Lagrange, the Hermit shouldn't be much more difficult to follow. One nice property of the Hermit is that along with interpolating at the data points, it also interpolates the derivative of the data points. In other words, the rate of change of whatever data set we are observing will also match up with the Hermit polynomial's rate of change. It's also worth noting that the Hermit is of degree 2n plus 1, and so we will only ever get odd degrees when using this interpolation method. Let's move on to see what the Hermit might look like graphically. Similar to the Lagrange polynomial that we constructed earlier, only 16 data points were used in creating the Hermit, and due to the nature of the Hermit being of degree 2n plus 1, we end up getting a polynomial of degree 33. As we can see on the plot in the top left corner, we are getting a lot of oscillation at the endpoints, just as we did for the Lagrange, which gives us an unrealistic depiction of the Snowfall data. But if we observe the data between 83 and 2011, seen in the bottom left corner, the Hermit looks really smooth, even smoother than the Lagrange. Unfortunately, we are still only using less than half of the data, and it would be nice if we could incorporate more of the data or all of it. So let's look at another interpolation technique and see if we can do a better job. The last interpolation technique we will be looking at is cubic spline interpolation, which is much different than the Lagrange or the Hermit methods we used earlier. The cubic spline is a piecewise function made up of different third-degree polynomials, which we call splines. The larger the data set, the more splines in the piecewise function. One nice property of using cubic spline interpolation is that we end up getting smoother curves throughout the function, which is especially nice when dealing with large data sets. Let's look at what these cubic splines look like graphically. Unfortunately, we are still seeing some unnatural behavior at the endpoints, as you can see on the graph, but we were able to create a function that incorporates all 51 Snowfall data points, which is really nice. On top of that, the polynomial looks relatively smooth throughout the entire data set, smoother than the Hermit or the Lagrange, and we weren't even using all the points. Again, unfortunately, with the odd behavior at the final data point, this cubic spline would likely not be a good fit for forecasting the data, but does a really good job over the 50 points. As far as forecasting the data, less points might be better. As previously mentioned, when using so many data points to create the interpolating function, we tend to get a lot of unnatural oscillation near the endpoints, which makes it hard to get a realistic forecast. Again, one solution might be using a much smaller portion of the data set, which is what I did here. This plot was extended out to 2071, but the drop in snow levels you can see on the end is likely just a side effect of the Lagrange polynomial and would probably not be realistic. I plan to continue assessing other ways to evaluate the snowfall data to make predictions in the future. So what were the project outcomes? Well, I was able to find several approaches to analyze the snowfall data, and each technique had different benefits. The cubic spline seems to be the best approach to analyze the snowfall data within the 50-year period. Unfortunately, I was not able to find a likely forecast for the snowfall data, but hope to continue working on this research independently in the future. Thank you for taking the time to let me share my research with you, and I hope you have a great day.